In the lecture, I already described the thermochemical processes of the biofuel energy generation. In my today's lecture, I want to describe the biochemical processes. In the previous lecture, I already described the thermochemical processes like the direct combustion process, pyrolysis process, and the other thermochemical processes. Today, I want to describe the aerobic digestion process and the anaerobic digestion process. In my next lecture, I want to describe the alcoholic fermentation process and the biophotolysis process and the two other agrochemical processes. The aerobic digestion process, the WAST is the natural biological degradation and purification process in which the bacteria that thrive in oxygen-rich environments break down and digest the waste. During the oxidation process, the pollutants are broken down into the carbon dioxide, water, nitrates, sulfates, and the biomass or the microorganisms. By operating the oxygen supply with aerators, the process can be significantly accelerated. Of all the biological treatment methods, the aerobic digestion is the most widespread process that is used throughout the world. The aerobic digestion process, the biological and chemical oxygen demand. The aerobic bacteria demands oxygen to decompose, dissolve the pollutants. Large amounts of pollutants require the large quantities of bacteria. Therefore, the demand for oxygen will be high. The biological oxygen demand or BOD is a measure of the quantity of dissolved organic pollutants that can be removed in biological oxidation by the bacteria. It is expressed in milligram per liter. The chemical oxygen demand or COD measures the quantity of dissolved organic pollutants that can be removed in chemical oxidation by adding the strong acids. It is also expressed in milligram per liter. The BOD or COD gives an indication of the fraction of pollutants in the wastewater that is biodegradable. The advantage of aerobic digestion. The aerobic bacteria are very efficient in breaking down the waste products. The result of this is the aerobic treatment usually yields better effluent quality that obtained in anaerobic process. The aerobic pathway also releases a substantial amount of energy. A portion is used by the microorganisms for synthesis and growth of the new microorganisms. The aerobic decomposition process, a biological process in which the organisms use the available organic matter to support the biological activity. These processes uses organic matter, nutrients, and dissolve the oxygen and produces the stable solids and the carbon dioxide and many more other microorganisms. The microorganisms which can only survive in the aerobic conditions are known as the aerobic organisms. In swirl lines, the swage becomes anoxic if left for a few hours and becomes anaerobic if left for more than 1.5 days. Anoxic organisms work well with the aerobic and anaerobic organisms. The facultative and the anoxic are basically the same concept. The anoxic decomposition, it is a biological process in which a certain group of microorganisms use chemically combined oxygen such as that found in the nitrite and the nitrate. These organisms consume the organic matter to support the life functions. They use organic matter combined oxygen from the nitrate and nutrients to produce the nitrogen gas and the carbon dioxide, stable solids, and the other more organisms. The second process is called the anaerobic digestion process. The combustible gas can also be produced from the biomass through the low temperature biological processes called the anaerobic digestion. That means the without air process. Anaerobic digestion is a complex biochemical reaction carried out in a number of steps by several types of microorganisms that require little or no oxygen to live. During this process, a gas that is mainly composed of methane and carbon dioxide, also referred to as the biogas, is produced. The amount of gas produced varies with the amount of organic waste fed to the digester, and temperature influences the rate of decomposition and the gas production. The biogas is the common name for the gas produced either in specifically designed anaerobic digesters or in landfills by capturing the naturally produced methane. The biogas is typically about 60% methane and 40% carbon dioxide with a heating value of about 55%, that of the natural gas. Almost any biomass except lignin, which is a major component of wood, can be converted to the biogas. The animal and the human waste, sewage sludge, crops residues, carbon-laden industrial processing byproducts, and the landfill material have all been widely used. The biogas generation is suitable for small to large scale operation. Rural systems in India mostly use the cow dung as input, but 1 million systems are urban, fed mainly on kitchen waste. The biogas may be used directly for domestic and process heat, for export to a utility gas, and possibly for lighting, and as a fuel for the engines and the electricity generators, with perhaps export to a utility grid. The anaerobic digestion process. First, the plant of the animal matter is decomposed by the bacteria into the molecules such as sugar. The decomposed matter is then converted to the organic acids, which are then converted to methane gas. The byproducts of the process include the methane gas and organic solids and liquids and small amounts of hydrogen sulfide gas, fuel to the gas grid as the biogas. And from the anaerobic digester, the digestate, which is used as the fertilizer, soil amendments, and the livestock bedding. The MB technologies systems help to remove the hydrogen sulfide gas from the methane. Following this process, both the biogas and the remaining organic solids and liquids can be used in multiple ways, presenting both the environmental and the basic process and the energetics of the anaerobic digestion process are described as the general equation for the anaerobic digestion in the input of the slurry is the CxHyOZ plus X minus Y by 4 minus Z by 2 H2O is equal to the x by 2 minus y by 8 plus z by 4 CO2 plus x by 2 plus y by 8 minus z by 4 CH4. For the cellulose, this becomes the C6H10O5N plus NH2O. It generates the 3NCO2 plus 3NCH4. The reactions are slightly exothermic, with typical heats of reaction being about 1.5 megajoule per kg dry digestible material, equal to about 250 kilojoule per mole of C6H10O5. That is called cellulose. This is not sufficient to significantly affect the temperature of the bulk material, but does indicate that most enthalpy of reaction is passed to the product gas. If the input material of the slurry had been dried and burned, the heat of the combustion would have been about 16 megajoule per kg. In complete anaerobic digestion, only about 10% of the potential heat of the combustion is lost in the digestion process, so giving the 90% conversion efficiency to the biogas. Moreover, very wet input is processed to give this convenient and controllable gaseous fuel, whereas drying the aqueous slurry would have required much energy, about 40 megajoule kg of the solid input. In practice, the digestion seldom goes to completion because of the long time involved, so 60% conversion is common. Gas yield is about 0.2 to 0.4 meter cube per kg of the dry digestible input at STP, with throughput of about 5 kg dry digestible solid per meter cube of the liquid. It is generally considered that the three ranges of temperature favor particular types of bacteria. Digestion at higher temperature proceeds more rapidly than the lower temperature, with gas yield rates doubling at about every 5 degree of the increase. The temperature ranges are as the psychrophilic about 20 degrees centigrade, mesophilic about 35 degrees centigrade, and the thermophilic is about 55 degrees centigrade. In tropical countries, the unheated digesters are likely to be at average ground temperature between the 20 and 30 degrees centigrade. Consequently, the digestion is the psychrophilic, with the retention times being at least 14 days. In colder climates, the psychrophilic processes is significantly slower, so it may be decided to heat the digesters, probably by using the part of the biogas output. A temperature of about 35 degrees centigrade is likely to be chosen for the mesophilic digestion. Few digesters operate at 55 degrees centigrade unless the purpose is to digest the material rather than the produced excess biogas. In general, the greater the temperature, the faster the process time. Now the anaerobic digestion occurs in 4 steps. The steps are hydrolysis, acidogenesis, acetogenesis, and the methanogenesis. In the hydrolysis, the complex organic matter is decomposed into the simple soluble organic molecules using the water to split the chemical bonds between the substances. Insoluble biodegradable materials like cellulose, polysaccharides and fats are broken down to the soluble carbohydrates and the fatty acids. This occurs in about a day at 25 degrees centigrade in an active digesters. complex organic matter, carbohydrates and protein and fats. Then the output will be the soluble organic molecules, sugar, amino acid and the fatty acid through the hydrolysis process. Now come to the second step, that is called the fermentation or the acidogenesis. In this process, the chemical decomposition of the carbohydrates by enzymes, bacteria, yeast or molds in the absence of oxygen blocker. Acid forming bacteria produce mainly the acetic acid and the propionic acid through the acidogenesis. This stage likewise takes about 1 day at 25 degrees centigrade. Then come to the third step, that is called the acetogenesis, where the acetic acid and the carbon dioxide is produced. The fermentation products are converted into the acetate, hydrogen and the carbon dioxide by what are known as the acetogenic bacteria. The acetogenic bacteria grow in close association with the methanogenic bacteria during the fourth stage of the process. The reason for this is that the conversion of the fermentation products by the acetogens is thermodynamically only if the hydrogen concentration is kept sufficiently low. This requires a close relationship between both the classes of the bacteria. Now come to the last step, that is called the methanogenesis. It is formed from the acetate and the hydrogen carbon dioxide by the methanogenic bacteria. The methane forming bacteria slowly in about 14 days at 25 degrees centigrade complete the digestion to a maximum of 70% of the methane and the minimum of 30% of the carbon dioxide with trace amounts of hydrogen and perhaps hydrogen sulfides. Hydrogen may play an essential role, and indeed some bacteria like the Clostridium are disinfective in producing hydrogen as the final product. The methane forming bacteria are sensitive to pH and conditions should be mildly acidic, where the pH is 6.6 to 7, but not more acidic than the pH 6.2. The nitrogen should be present at 10% by mass of the dry input and the phosphorus at 2%. A golden rule for the successful digester operation is to maintain constant conditions of temperature and suitable input material. Consequently, a suitable population of the bacteria becomes established to suit these conditions. Now come to the topic at biodigesters. The most important types of biogas plants are the fixed dome plants, which is shown in the figure. Second is the floating drum plants. This is the floating drum plants. Third is the balloon type plants. This is the balloon type plants. Fourth is the horizontal plants. Fifth is the earth pit plants. And the last is the ferro cement plants. Now come to the fixed dome plants. The cost of a fixed dome biogas plant are relatively low. It is simple, so no moving parts exist. There are also no rusting steel parts, and hence a long life of the plants, approximately 20 years or more, can be expected. The plant is constructed underground, protecting it from physical damage and saving the space, while the underground digester is protected from low temperatures at night and during the cold seasons. Sunshine and warm seasons can take longer to heat up the digester. There are number one in the shown in the figure is the mixing tank. The cow dung is collected from the shed and mixed with the water in equal proportion 1:1 to make a homogeneous mixture in the mixing tank. Number 2 is the digester. The fed slurry is subjected to the anaerobic fermentation with the help of the microorganisms inside the digester. Third is the compensation and the removal tank, that is called the slurry outlet tank. 3. This is the digested slurry is let out from the digester through the slurry outlet pipe. 4 is the gas holder. This is the 4 is the gas holder. As a result of the anaerobic fermentation, the gas produced is stored in the gas holder. 5 is the gas pipe. This is the gas pipe, the gas outlet pipe actually. So the stored gas is released and conveyed through the gas outlet pipe present at the top of the gas holder. Then 6 is the entry hatch with the gas tight seal. This is the seal. 7 is the accumulation of the thick sludge. 7 is the accumulation of the thick sludge. 8 is the outlet pipe. This is the outlet pipe. 9 is the reference level. This is the level of the reference level. And 10 is the supernatant scum broken up by varying the level. This is the 10. So now no day and night fluctuations of the temperature in the digester positively influence the bacteriological process. The construction of fixed dome plants is labor intensive, thus creating the local employment. Fixed dome plants are not easy to build. They should only be built where the construction can be supervised by experienced biogas technicians, otherwise the plants may not be gas tight. The basic element of the fixed dome plant are shown in the figure. Now come to the fixed dome plant function. A fixed dome plant comprises of a closed dome-shaped digesters with an immovable rigid gas holder and a displacement pit, also named the compensation tank. This is the mixing pit. This is the digester. This is the gas holder. This is the displacement. 4 is the displacement pit. And 5 is the gas pipe. The gas is stored in the upper part of the digester. When the gas production commences, the slurry is displaced into the compensating tank. Gas pressure increases with the volume of gas stored, such that with the height difference between the two slurry levels. If there is little gas in the gas holder, the gas pressure is. The digesters of fixed dome plants are usually masonry structures of the cement and the ferrocement exist. Main parameters for the choice of the materials are the technical suitability, that is stability, gas and liquid tightness, cost effectiveness, availability in the region and the transport cost, availability of the local skills for working with the particular building material. The fixed dome plants produce just as much as floating drum plants if they are gas tight. However, the utilization of the gas is less effective as the gas pressure fluctuations substantially. Burners and the other simple appliances cannot be set in an optimal way. If the gas is required at constant pressure, a gas pressure regulator or a floating gas holder is necessary. The top part of the fixed dome plant must be gas tight. Concrete masonry and the cement rendering are not gas tight. The gas space must therefore be painted with a gas tight layer, should be waterproof. Latex or the synthetic paint should be used. A possibility to reduce the risks of the cracking of the gas holder consists in the construction of a weak ring in the masonry of the digester. This ring is a flexible joint between the lower and the upper part of the hemispherical structure. It prevents the cracks that develop due to the hydrostatic pressure in the lower parts to move into the upper parts of the gas holder. Now come to the classification of the fixed dome plants. The Chinese fixed dome plants as shown in the figure, which is the archetype of the all fixed dome plants. The several million have been constructed in China. The digester consists of a cylinder with round bottom, the top. The following aspect must be considered with the regard to design and operation. An overflow into and out of the compensation tank must be provided to avoid the overfilling of the plant. The gas outlet must be located about 10 cm higher than the overflow level to avoid the plugging up of the gas pipe. The plant must be covered sufficiently with the soil to provide an adequate counter pressure. Special care must be taken to properly close the manhole, which may require to weight down the lid with 100 kg or more. The safest method is to secure the lid with the clamps. The following structural measures are recommended to avoid the cracks in the gas holder. The foot of the dome should be stabilized by letting the foundation slab project out enough to allow for an outer ring of the motor. A rated brake or the pivot ring should be provided at a point located between half and 2/3 of the minimum slurry level. This in order to limit the occurrence or the propagation of the cracks in the vicinity of the dome foot, and to displace the forces through its stiffening or the articulating effect such that the tensile forces are reduced around the gas space. Alternatively, the lowest point of the gas holder should be reinforced by a steel ring, or the whole gas holder be reinforced with the chicken mesh wire. Normally the masonry, the mortar and the concrete are not the gas tight with or without mortar additives. Gas tightness can only be achieved through the good, careful workmanship and the special coating. The main precondition is that the masonry and the plaster are strong and free of cracks. Cracked and the sandy rendering must be removed. In most cases, a plant with the cracked masonry must be dismantled because not even the best seal coating can render cracks permanently gas tight. So tried and the proven seal coats and the plasters. The multi-layer bitumen applied cold 2 to 4 thick coats required. Bitumen with the aluminium foil, thin sheets of overlapping aluminium foil may be applied to the still sticky bitumen, followed by the next coat of the bitumen. The plastics, example of the epoxy resin or the acrylic paint, very good but expensive. So the paraffin or the diluted with the 2 to 5% kerosene, heated up to 100 degrees centigrade and applied to the preheated masonry, thus providing an effective seal. In any case, a pressure test must be carried out before the plant is put in service. Fixed dome plants must be covered with the earth up to the top of the glass filled space to counteract the internal pressure up to 0.15 to 15 bar. The earth cover insulation and the option for internal heating makes them suitable for colder climates. Due to the economic parameters, the recommended minimum size of the fixed dome plant is the 5 meter cube in size. The digester volumes up to 200 meter cube are known and possible. The second type is called the Janata model. The Janata model was the first fixed dome design in India as a response to the Chinese fixed dome plant. Developed by the Research and the Action Division, Lucknow in 1978 in India. It is not constructed anymore. The mode of the construction lead to cracks in the gas holder. Very few of these plants had been gas tight. The digesters is cylindrical in shape, constructed with the bricks and cement material other than the cattle dung such as municipal waste and the plant residues. The dia ratio height is 1.75:1. Third is the Dinabandhu. The successor of the Janata plant is shown in the figure, which is produced in India with improved design, was more crack proof and consumed less building material than the Janata plant with a hemisphere digester. Fourth one is the Kamartek model. Has a simplified structure of a hemispherical dome shell based on a rigid foundation, ring only and a calculated joint of the fraction, so called the weak or the strong ring. It was developed in the late 80s in Tanzania. Next one is the acute fixed dome plant, which is an improvement of the above mentioned Nicaraguan design. Digester volumes ranges from 8 to 124 meter cube with the gas storage from 2 to 19.4 meter cube. The gas production can reach 60 meter cube per day. The units from 32 meter cube onwards are open used for small scale productive use including the electricity generation. It has a cylindrical base with a spherotic top. The expansion chamber acts as the overpressure outlet. Last one is the acute Mendeleo adds a gas storage balloon to collect the excess gas from the digester chamber, which is shown in the figure. This can be used for the converted diesel generators. Now the advantages and disadvantages of the fixed dome plants. The advantages are the low initial cost and the long useful lifespan, no moving or rusting parts involved. Basic design is compact, saves space and is well insulated construction creates local employment. Disadvantages: the masonry gas holders requires special sealant and gas technical skills for the gas tight construction. Gas leaks occur quite frequently. Fluctuating gas pressure complicates the gas utilization. Amount of gas produced is not immediately visible. Plant operation not readily understandable. Fixed dome plants need exact planning of the levels. Excavation can be difficult and expensive in the bedrock. The fixed dome plants can be recommended only where the construction can be supervised by experienced biogas technicians. Now come to the floating drum plants. The drum in the past, the floating drum plants were mainly built in India. A floating drum plant consists of a cylindrical or dome-shaped digester and a moving floating gas holder or drum. The gas holder floats either directly in the fermenting slurry or in a separate water jacket. The drum in which the biogas collects has an internal or an external guide frame that provides the stability and keeps the drum uptight. This is the floating gas holder. This is the outlet of the biogas. This is the mixing tank, slurry or the cattle dung and water. This is the inlet pipe to the digester. This is the underground digester tank. This is the partition wall. This is the outlet of the gas, and this is the separation or the overflow tank is there. Now come to the guide frame. The guide wall of the gas drum should be just as high as the wall above the support ledge. The floating drum must not touch the outer walls. It must not tilt, otherwise the coating will be damaged or it will get stuck. For this reason, a floating drum always requires a guide. This guide frame must be designed in a way that allows the gas drum to be removed for repair. The drum can only be removed if air can flow into it, either by opening the gas outlet or by emptying the water jacket. The floating gas drum can be replaced by a balloon above the digester. This reduces the construction cost, but in practice problems always arise with the attachment of the balloon to the digester and with the high susceptibility to the physical damage. The size: the floating drum plants are used chiefly for digesting animal or human feces on a continuous feed mode of operation, such that with the daily input. They are used most frequently by small to middle-sized farms. Digester size should be 5 to 15 meter cube, or in the institutions and the larger agro-industrial estates, the digester size should be 20 to 100 meter cube. The materials of the digester and the drum: the digester is usually made of brick, concrete or quarry stone masonry with the plaster. The gas drum normally consists of 2.5 mm steel sheets for the sides and 2 mm sheets for the top. It has welded in braces with break-up surfaces come when the drum rotates. The drum must be protected against corrosion. Suitable coating products are well paints, synthetic paints and the bitumen paints. Correct priming is important. There must be at least 2 preliminary coats and the one top coat. The coating of used oil is very cheap. They must be renewed monthly. Plastic sheeting stuck to bitumen sealant has not given good results. In coastal regions, the repainting is necessary at least once a year, and in dry uplands at least every other year. Gas production will be higher if the drum is painted black or red rather than blue or white, because the digester temperature is increased by solar radiation. The gas drums made of 2 cm wire mesh reinforced concrete or fiber cement must be receive a gas tight internal. The gas drum should have a slightly sloping roof, otherwise the rainwater will be trapped on it, leading to rust damage. An excessively steep pitched roof is unnecessarily expensive, and the gas in the tip cannot be used because when the drum is resting on the bottom, the gas is no longer under pressure. The floating drums made of glass fiber, reinforced plastic and high density polythene have been used successfully, but the construction costs are higher compared to the using steel. Floating drums made of wire mesh reinforced concrete are liable to hairline cracking and are intrinsically porous. They require a gas-tight elastic internal coating. PVC drums are unsuitable because they are not resistant to use. There are different types of floating drum plants. The KVIC model. The KVIC model with a cylindrical digester, the oldest and the most widespread floating drum biogas plant from India. The Khadi and the Village Industries Commission model this type of digester. For this reason it is named as KVIC. It is developed in India in 1954. Mild steel drum is used for collecting the gas. Costliest component is the gas holder. Having lived less than 10 years of the gas holder, the material used cow dung in this plant for producing the gas. Second is the Pragati model with a hemisphere digester. It is developed by United Socio-Economic Development and the Research Program. It is cheaper floating drum biogas plant. Depth of pit is less than KVIC plant. It can be constructed in hilly and the higher water table areas. Cost of this plant is 20% less than the KVIC plant. Third one is the Ganesh model. The Ganesh model made of angular steel and plastic foil floating drum plant made of prefabricated reinforced concrete compound units. Floating drum plant made of fiberglass reinforced polyester. Fourth one is the Boda model. The Boda plant combines the static advantage of the hemispherical digester with the process stability of the floating drum and the longer lifespan of a water jacket plant. The advantages of the floating drum plants. Floating drum plants are easy to understand and operate. They provide gas at a constant pressure, and the stored gas volume is immediately recognizable by the position of the drum. Gas tightness is no problem provided the gas holder is derusted and painted regularly. But there is some disadvantages also. The steel drum is relatively expensive and maintenance intensive. Removing rust and painting has to be carried out regularly. The lifetime of the drum is short, up to 15 years. In the tropical coastal regions, about the 5 years. If fibrous substrates are used, the gas holder shows a tendency to get stuck in the resultant floating. The low-cost polythene tube digester, that is called the horizontal plant, as shown in the figure. In the case of the low-cost polyethylene tube digester model, which is applied in Bolivia, the tubular polyethylene film, 2 coat of the 300 microns, is bended at each end around a 6-inch PVC drain pipe and is wound with the rubber strap of the recycled tire tubes. With this system, a hermetic isolated tank is obtained as shown in the figure. Next one is the tube digester, that is the horizontal plant. One of the 6 inches PVC drain pipes serves as the inlet and the other one as the outlet of the slurry. In the tube digester, finally a hydraulic level is set up by itself so that as much quantity of added prime matter, that is the mix of the dung and the water, as quantity of the fertilizer leave by the outlet. Because the tubular polyethylene is flexible, it is necessary to construct a cradle which will accommodate the reaction tank so that a trench is excavated. The capacity of the gas holder corresponds to 1/4 of the total capacity of the reaction tube. To overcome the problem of the low gas flow rates, 200 microns tabular polyethylene reservoirs are installed close to the kitchen, which gives a 1.3 meter cube additional gas storage. Next one is the balloon digester. A balloon plant consists of a heat-sealed plastic or rubber bag combining digester and gas holder. The gas is stored in the upper part of the balloon. The inlet and the outlet are attached directly to the skin of the balloon. Gas pressure can be increased by placing the weights on the balloon. If the gas pressure exceeds a limit that the balloon can withstand, it may damage the skin. Therefore, the safety valves are required. If the higher gas pressures are needed, a gas pump is required. Since the material has to be weather and UV resistant, specially stabilized, reinforced plastic or synthetic couch is given preference. Other materials which have been used successfully include the RMP, that is called the red mud plastic, Trivera, and the butyl. The useful lifespan does usually not exceed 2 to 5. The advantage of the balloon digesters are standardized prefabrication at low cost, low construction sophistication, easy of transportation, shallow installation suitable for use in areas with a high groundwater table, high temperature digesters in warm climates, uncomplicated cleaning, emptying and maintenance, difficult substrates like water, hyacinth can be used. Balloon biogas plants are recommended if the local repair is or can be made possible and the cost advantage is substantial. The disadvantages of the balloon digesters are the low gas pressure may require gas pumps, scum cannot be removed during the operation, the plastic balloon has a relatively short useful lifespan, and is susceptible to the mechanical damage, and it is usually not available locally. In addition, the local craftsmen are rarely in a position to repair a damaged balloon. There is only little scope for the creation of the local employment and therefore limited self-help potential. Now the next one is the fifth one is the earth pit plant. The masonry digesters are not necessary in the stable soil. It is sufficient to line the pit with a thin layer of cement in order to prevent the seepage. The edge of the pit is reinforced with a ring of masonry that also serves as anchorage of the gas holder. The gas holder can be made of metal or plastic sheeting. If the plastic sheeting is used, it must be attached to a quadratic wooden frame that extends down into the slurry and is anchored in place to counter its buoyancy. The requisite gas pressure is achieved by placing the weights on the gas holder. An overflow point is in the peripheral wall serves as the slurry outlet. The advantages of the earth pit plant is the low cost of installation, high potential for self-help approaches. Some disadvantages are there: the short useful life, serviceable only in suitable impermeable types of soils. Earth pit plants can only be recommended for installation in impermeable soil located above the groundwater table. Their construction is particularly expensive in connection with the plastic sheet gas holder. Last one is the ferrocement plants. The ferrocement type of construction can be applied either as a self-supporting shell or an earth pit lining. The vessel is usually cylindrical. Very small plants can be prefabricated. As in the case of a fixed dome plant, the ferrocement gas holder requires special sealing measures, proven reliability with the cemented on aluminium. Some disadvantages of the ferrocement plants, that is the substantial consumption of the essentially good quality cement. Workmanship must meet high quality standards. Uses substantial amounts of expensive wire mesh. Construction technique not yet adequately time tested. Special sealing measures for the gas holder are necessary. Ferrocement biogas plants are only recommended in cases where the special ferrocement know-how is available. Now the comparative study of the different types of biodigester in a summary table. The gas storage in the fixed dome is the internal gas storage up to 20 meter cube. In the floating drum, the internal gas storage drum size is very small. In the tubular design, the internal eventually external plastic bags. For the plastic containers, the internal gas storage drum sizes is very small. Durability, the very high for the fixed dome is greater than 20 years. Floating drum is high but drum is weakness. Tubular, it is medium depending on the chosen liner. For the plastic containers, that is the medium. Sizing for the fixed dome is 6 to 124 meter cube digester volume. For floating drum up to 20 meter cube. For tubular design, it is combination is possible. For the plastic, it is up to 6 meter cube digester volume. Methane emission, biogas emission for the fixed dome is very high. Floating drum is medium. Tubular design is low, and the plastic container is medium. Now the anaerobic digestion process, there is some environmental benefits. Protect the animal and the human health by reducing the pathogens. Convert the nutrients in waste into the more accessible forms for plants to use compared to the raw manure, thereby increasing the crop productivity and yields. Recycle nutrients on the farm, creating an economically and environmentally sustainable food production system, produce heat, electricity or fuel from the biogas which can be used on site, lessening the agriculture sector's dependence on the fossil fuel energy. Accept the food waste from the places like restaurants and grocery stores. This means the less food waste is sent to the landfills. Food waste has the added benefit of the increasing the efficiency of the farm digestion. There is some economic benefits. The construction and the operation of the digesters creates local job opportunities and increases the local tax revenue, presenting opportunities in the several forms. The local contractors specializing in site work, concrete, plumbing, electrical, permitting and engineering during the planning and construction phase of the operations. Skilled laborers to keep the system functioning at optimal levels once completed and operations. Businesses specializing in nutrients, manure, solids and energy markets. Agrotourism, whereby the visits of the farms allow guests to learn about the environmental improvements and the source of their food. This is the end to my today's lecture. These are the references from which I make the lecture. Thank you.